All right, here we go. So, guys, one more time. Laptops down. Okay. Thank you. So we're going to take a couple minutes of notes on water. If you have your reading guide right in front of you, you can kind of maybe just emphasize certain parts of water. That's just mainly because some of it is repetitive, but I want to make sure we're making connections between the two, chapter 15 and chapter 16. Before I start with this for just a minute, I need to hit some highlights of what I'm expecting for your selfies with scientists. So, raise your hand if you feel like you and your partner are like 100% on the same page. 100%.
Me too.
Okay, that's good, but that's not everybody, right? And so I know that we all have those projects where, you know, one person's holding down 75% of it, and the other person's holding down 25. We've all been the person where we were 75. We've all been the person where we were 25. And it's not, it's not something that you want to linger for long, because when you choose to work with somebody, you want to be good friends after the project. You don't want to be enemies. And this is a test grade, right? Projects are test grades. So one thing, I want to make sure you're 100% communicating with each other. You're communicating with me and your professional. So if your professional has emailed you back and you have not emailed them back within 24 hours to 48 hours, no, that's not respecting their time. They're not going to take you seriously, and they're not going to give you the respect that you deserve, because you're coming at them with a really honorable project to make sure that you're reaching outside of the educational field to see where this stuff is important in real life. Okay, give them the time of day. Email them back. Second, everything should be on Google Docs, just so I can find your tabs. I'm doing a good job of going back and checking things if you're not emailing me, but like Emma said, hello, checking questions via text today, because that prompted me to go back and look, because it doesn't always update me when you make a change, right? It needs to be clear that you need me to go back and check things. And it's not a divide and conquer kind of thing, guys. I know that makes it easy. Like, you make 5 questions, I make 5 questions, I'll do the poster, you do the paper. This seems to be like a true collaboration. So, like, your schedules are crazy. Choose a day where you're like, okay, let's analyze what this person said via the interview. Okay, let's sit down and let's like knock out those questions, this layout of paper together. All right, let's sit down and like knock the poster together. It's okay to do many parts from each other, like away from each other, but try to keep it collaborative, because that's the beauty of a partnership. It's not a partnership if it's just, I'm in the same room as you, and you're doing half of it, and I'm doing half of it. That's not really a partnership. You see how that's different? Working in a group should be a collaborative activity. You should be communicating. You should be like working together and like problem solving together. All right. All right. So laptops are down. Thank you. All right. So we're gonna watch a quick video on water, and from here, well, one of these tabs. No. But if you take some time to read and think about what you're doing, you should internalize some of that, which is why you don't always have the right questions. All right, so we'll be right back. Write down, if you wish, a couple of things, but there's not like more than what was in your reading guide necessarily.
Life, as we know it, would not exist without water. Over 70% of the planet is covered in water, and our bodies are around 70% water. But why is water so important? The structure of a water molecule and the fact that it is capable of forming hydrogen bonds with multiple other water molecules simultaneously provides water molecules with some very unique characteristics. These include the ability to act as a universal solvent, the properties of cohesion and adhesion, a high surface tension, a high...
This is pretty valuable. Either add it, okay, one more time. Laptops are down. You're either writing this on your reading guide or maybe making little notches on your reading guide like, oh, I saw this is relevant here, or internalizing. Okay, make a choice. Thank you. So universal solvent, cohesion, adhesion, and high surface tension, and high heat capacity. One more.
A heat capacity, and changes in density based on temperature. Let's take a look at each of these in turn. Water is often called the universal solvent, which means that many substances dissolve in it. Water's solvency has to do with the polarity and hydrogen bonding ability of water molecules. When a salt, such as sodium chloride, is placed in water, the negative ends of the water molecules are attracted to the positively charged sodium ions, and the positive ends of the water molecules are attracted to the negatively charged chloride ions. This attraction causes the sodium and chloride ions to break up, or dissociate in water. Why is this important? Since our cells are mostly water, these solutions of ions and molecules allow chemical reactions to occur much more frequently, which is an important feature to allow organisms to respond to their environment.
All right, one quick question. Is the red one or the grayish colored one oxygen? The red one, right? Big O oxygen right there. We've got a high electronegativity on the, remember, do the little finger trick with the pure oxygens. Okay, you got it? I'm not going to show you how to do it. I see one person doing it. Right hand radius, right? So your right hand does what? Okay. And then your left hand just kind of completes the little square. Your right hand is your radius. So who's the biggest one on the periodic table? Francium, right? It's to the left and down. It's not just to the left. And who's the most electronegative? Negativity. Most electronegative.
Helium?
No, not helium. Helium's a double gas. It doesn't want any more electrons. Fluorine, good. So fluorine and oxygen's right next to that, hence why it has a negative charge. And then the two hydrogens have the partial charges positive. Sodium is positive, so why does it? Why does this oxygen next to it? Good, opposites attract. And then why is chlorine next to the hydrogens? Opposites attract. That should be very clear. There was a question like this on the exam last year, year before. It had like a drawing, and you had to identify which was represented by which, and tell why the question. I mean, why the one side was attracted to the other side. So.
Water molecules are also cohesive and adhesive. The hydrogen bonds in water cause water molecules to stick together, a property known as cohesion. Polar bonds also give molecules an adhesive property, or the ability to cling to other polar surfaces. Why is this important? Well, water fills the internal transport systems of plants and animals. Because of these cohesive and adhesive properties, water allows for the efficient transport of nutrients and waste within an organism. Water also has a high level of surface tension. Because water molecules at the surface are more strongly attracted to each other than to the air above, water molecules...
What is this blue stuff they were trying to represent? The hydrogen bonds. Are hydrogen bonds real bonds? No, they are simply attractions, right? So the H's from this first water is attracted to the O of the second water. The H's from the next water is attracted to the O of the second water, and so forth. It's like a little magnetic attraction all the way through. But could I pull the water molecules apart? Totally, yeah. Like, it's just an attraction. It's not like a bond. It's not locked in there forever. So it's just saying those are more attracted to each other, which is why we're going to have some surface tension. Yeah.
All right, so that line right there is the surface tension?
Yep. It's the surface water molecules that are highly attracted to each other, but not attracted to the air. So that's a very strong attraction they have to themselves and to underneath, but just not above. Because air is a covalent molecule and it doesn't attract to the water quite as well.
Cling tightly to each other. The surface tension of water explains why it beads up on waxy surfaces and why water-striding insects are able to walk on the surface of water. Water has a high capacity for heat. What this means is that the many hydrogen bonds that link water molecules let water absorb a large amount of heat without changing its chemical state, for example, from liquid to gas. This not only stabilizes the temperature of bodies of water, such as lakes and oceans, but also plays an important role in the physiology of an organism. Since life is based on water, and the temperature of water rises and falls slowly, living organisms are better able to maintain their normal internal temperatures and are protected from rapid temperature changes. And finally, the density of water is based on its temperature. However, unlike many other compounds which contract when they freeze, the configuration of the hydrogen bonds in water causes it to expand when it freezes. This expansion causes ice to have a lower density than liquid water, and therefore ice floats on liquid water. If ice were more dense than water, it would sink.
What are these little blue lines? Hydrogen bonds, hydrogen bonds, hydrogen bonds, right? That's causing all the properties of water. That is a key word that you should always associate with water and anything else that's associated through a O or H to N or F bond. Yeah.
Is that all of the shapes and the crease, or did they just...
That actually is. It's a more of a hexagonal pattern that ice takes on. So like 6 water molecules kind of become kind of in a lattice in themselves. What's in the middle of this, guys? What's right here? Nothing. Nothing. There's a big, maybe if anything it might be an air pocket, but there's nothing there. So it's expanding because it's taking up more space, but is there more volume in that space? I mean, is there more matter in that space? No, which is why ice floats, because it's low density. Yeah.
So hydrogen bonds in liquid water are only present on the surface?
No, hydrogen bonds are present everywhere, everywhere, everywhere. Actually, so like they don't have them all drawn down here because they're kind of scattered. It's got a high disorder. This is very ordered, so it's showing you how it's ordered. It's ordered because the hydrogen bonds are very, they're moving slower, so they kind of are more, they have higher magnitude because they're moving slower. These are moving faster, so the hydrogen bonds are kind of weakly there. Good questions.
And ponds and lakes would freeze solid, making life there impossible. Instead, bodies of water always freeze from the top down. The ice on the surface acts as an insulator to protect the water below from freezing. This protects aquatic organisms so that they can survive the winter.
And that's why we can go ice fishing. All right, very good. Go ahead and quick review. Talk to the person next to you. Tell them what you know or write down what you know about water.
Could I please have Evan Briskman for dismissal? Thank you.
Water? Spent.
Oh, okay.
Collectively, yeah. Oh, yeah. Oh, good.
They are able to
All right, come back to me. 3, 2, 1. Raise your hand if you can tell me the empirical formula. Everybody knows the empirical formula of water. H2O, thank you. Guys, all right, back to me. What's the molar mass of water? 18-ish grams per mole. Good. Is it ionic or covalent? H2O. What kind of atoms are within this? Non-metal? Non-metal. I know H is in the first alkali metal group, but it is certainly not a metal. It's going to be a non-metal, right? So this is going to be all covalent. And then is it a polar covalent molecule or is it a non-polar covalent molecule? It's polar because it has a what shape? And why does it have a bent shape? No, because it's polar. Sorry, it's polar because it's bent, but why is it bent?
Because the positives are going away from the positives. They're pushing against each other.
So, I mean, I could draw it like this, right? But I didn't. And it's because of this little guy right here. What are these? And these lone pairs are negative. So what are they doing with this bonded pair?
Oh, they're
Pushing.
They're repelling, thank you. So they're repelling it down. It's like negatives on negatives on negatives. So they're all going to be pushing everything down away from each other, which is why it has this overall bent shape. This up here is very partially negative. Hydrogens have no electrons, so they're partially positive, which is how we get that opposite ends polar look to it. Oh, so now we know it's molecular geometry. Bent. This is polar. And then we already know a lot of its properties. These are 5 of which you should know. Okay? So we do water in a nutshell because water is something we've talked about all year. It's just making sure we're clear on like how we take the chemical nature of it relating to the physical nature of it. What do you need?
I was just talking about
Okay, got it. Good? Okay. Quick, you have like 3 seconds. What IMF holds water molecules together? Okay, so we know that is the key word for water. And yep, we got all that. What shape is this one more time? Then these are the what?
hydrogen.
Hydrogens. This is the, and I say that because we keep drawing water wrong every time. 2 O's and an H. H2O, okay? It's alright, you just take some practice. Ooh, ah. Okay, thank you. Hydrogen bonds in action. This is just a quick reminder of the surface tension. What's happening on this bottom? Actually, what's happening all around the entire surface of this molecule?
The pressure on the
Well, what's happening with the water all around here?
they're bonding.
They're bonding how? With hydrogen bonding to make a little spherical shape. But then there is some pressure, like there's air pressure up here, which is why it's not a perfect circle. It's kind of a flat, kind of oblong shape. But if you're on Mars, gravity and air pressure would be different, or out in outer space, they would be like perfect spheres. Okay. Yes.
So
Start rating.
if it wasn't like the air pressure, whatever, about the surface tension, like say like spraying a hose or something, like would it just like kind of just go off crazy? Would it be like kind of like this?
Or you mean very like tight blisters? Yes.
Alright.
Air pressure goes along. Okay. So as you're writing, just raise one hand if you've ever used soap.
This side.
Oh Lord. Okay. So we know that soap does a lot of has a lot of chemical reactions within it. It also has some chemical reactivity with other things. There's actually a very special property that soap has that many other things don't. And it's that it has a polar end and a non-polar. And because of that, we call it a surfactant. So let's get those terms down first. So the surfactant nature of soap and detergents and I think what else do you clean things with? Face, yeah, shampoo, face wash, liquid dish soap. Can you think of anything else you clean things with?
What about like the tablets you put in the
Those are detergents. I mean, that's all they are. They're just solidified. Bleach is going to be its own, like, it's sodium hypochlorite. It's not really a cleaning agent like a surfactant. So all of those things we clean stuff with are considered surfactants because what they do is normally you can clean things with water plus soap, right? But water likes water. Water likes it's hydrogen bonded to itself. It likes itself a whole lot. It doesn't always like to mess with dirt and grime and grease because dirt and grime and grease is all non-polar and water is polar. Polar things like to mess with polar things. Non-polar things like to mess with non-polar things. So how do we get water to mess with grease? Like how do we get it to interact?
Yeah.
You add something to break up this hydrogen bonds, right? You add a surfactant, and that's what soap serves. It breaks up all the hydrogen bonding of water, and it's like, water, you're going to interact with this grease, and you're going to wash it down the sink. Or take the dirt out of the clothes and wash it down the washer. So it just basically interferes with the ability to attract to itself, so it will interact well with other things it normally doesn't play nicely with. And that's because that's because soap, there's a picture, can you guys see this one?
Yeah.
Okay, it's kind of hard to see. But this is soap, and this is soap interacting with oil. But basically, there's this section here that is a hydrocarbon. Okay, so this section that looks like this is all carbon to hydrogen. So would you say that is a polar or non-polar region?
Oh.
It's all kind of covalent, it's all non-polar. Okay, and then this SO4 2 minus, I'll say. Ooh, what's that? Sulfate, right? Sulfate is an ion, and ions interact well with water because they're charged, so they have more of a polar characteristic. So this side over here interacts with water, and this side over here interacts with oil, and so it does a good job of pulling them together so they interact, so they can be clean. Question?
So you have one of those like water bottles out of like the oil in the water and everything. So if you put a little bit of soap in that, would it all like?
Oh, it all mixed together. It would look horrible. It would be cloudy and
Really?
junky. No, you ruined my perfect little lava
I don't
lamp.
know where it went.
It's in the back. I don't have it out right now.
Like,
So that's it for chapter 15. Water. That's only for today. That's it for chapter 15. Okay. So here are my quick jokes for you. Quick jokes. I'm sorry. We just can't be together. Is it because I'm fat? Okay, because this is what Carbon, 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 carbon. Think CHO. No. Lipids in biology, all carbon, hydrogen based. And this is water, and it's polar. This is non-polar. They can't be together. Okay. Anyway, good joke, Inlo. Sorry. I thought I would break the tension. Boom, boom. That one over there. Yeah. Okay. Oops. And then, help, help! I'm dissolving. My bears are insoluble. That's easy for you to say. You're not polar.
Yeah, we saw that. Why is that grizzly bear?
It's because it's still relevant. That's not a polar bear. That's a polar bear.
No, I'm saying, why is the grizzly bear with the bull?
He tossed him in the water. You see that? Look at her face. Okay. And then name's bond, hydrogen bond. Great. Thanks, guys. You're very easy to please. All right, take a minute, write that down.
40 years ago, I was in here back and watching these videos and shows this.
You can tutor people with these videos.
Oh, yes.
All right. Read, write. Read, write. Oh, another an example of a surfactant is whatever makes mayonnaise, because it's oil and eggs. Oil and eggs don't necessarily mix really well together. You add an emulsifier. It's related to being a colloid.
Wow, look at you. You know a lot about mayonnaise. Always weak. Remember when I thought I was scared? I wanted him to do it one time, I forgot so bad, and he wouldn't do it.
Well, you don't get those.
Okay, so we kind of know what solubility is. So we did a reading guide, we did that interactive to understand that there's a lot of stuff that can go into solution, but does it all dissolve?
No.
No. So you have sweet tea, you have sugar, like 1 or 2 teaspoons. Is it going to dissolve? Maybe, like probably, a couple spoonfuls, yeah. But if you add like 2 or 4 cups of sugar into like a pitcher, you're going to have sludge. You're going to have like a big sludge of sugar in the bottom. It's not going to dissolve. Okay, so there's that nice diabetes in the bottom of the liters, okay?
I don't shoot diabetes.
So what we have here is an idea that, yes, things will dissolve, but there's a capacity for dissolving. Things are going to dissolve infinitesimally, if that's the word, right? It's not going to keep on dissolving, keep on dissolving, keep on dissolving. There's going to be a point where it's, quote, saturated. But what we should know is, like, what is solubility, right? We're taking what, we're putting it in what? Solute to put it in a solvent to make a solution, right? So we should know those words, and we should be clear on, like, if we could have a picture in our mind of what a solute is versus a solvent. Who's the universal solvent? Water. So a lot of the time we're going to be talking about an aqueous solution, which aqueous means what? Dissolved in water, right? So we'll be talking about aqueous solutions quite a bit. All right, so the solubility, though, of a solution can differ across all solutions. Different things dissolve more than others. Like sodium chloride could dissolve quite well, where sucrose may not dissolve quite well. So we can have a difference in solubility across all types of solutions. And I do have to make sure that we're talking about a specific temperature and pressure, because as you guys saw in your reading, temperature changes the amount of things that can be dissolved. What's the general rule of thumb for increasing temperature? It should increase the solubility of solids, but gases, on the other hand, act a little funny. And under different pressures, you can have more or less dissolved or something. So we have to kind of clarify that at a specific temperature and pressure. What we say is, and I'm going to show you a picture now, do be clear that we are talking about solubility in a certain unit. So what we'll see is on a graph shortly is that it's grams of solute per 100 grams of solvent. We do have to make sure it's clear that these are all for solids, and that for gases we usually use per liter because there's like not as many gases dissolved per liter. So in this diagram here, what it's trying to show you is that here's your big chunk of a crystal, of salt crystal you've dumped into a solution, and as these, like this cation dissolves, water surrounds it, right?
But technically, I'm going to draw this the other way, another ion could go back into the crystal and kind of precipitate on itself. So there's this dynamic equilibrium of dissolving, precipitating, dissolving, precipitating, and it's a constant battle where the ions are trying to dissolve, but then some of them go back into the crystal form. So that's why you need to understand that a saturated solution is not stagnant. It's not just sitting there. There's stuff happening on the microscopic level. Does that picture help demonstrate that? Yes? Okay. So we're going to scooch in. Okay. These are your terms. You're supposed to elaborate on that a little bit more in your saturated, unsaturated potable. This hopefully will clarify that. We should be writing these terms down now, okay? Oh, more concentration. Classification of solutions by concentration, yeah. Conc is concentration. Precipitate. I'm going to pass by a couple things so you guys can make sure we grab some. PBT means precipitate. If there are extras, just leave them in the lab station, so I'll grab them. You do one? No, I'm sorry. I said take one and pass it back. It's your lunch. Give me a thumbs up when you have your definitions down. Okay, we're seeing where we are. Alright, so quick explanation, like simplest word you can think of, saturated. Give me one word.
Full.
Full. That's it. That's it. Full. It is full of solute. It cannot hold any more solute in a dissolved state. You can keep adding solute, but where is it going to go in solution? Straight to the bottom, make a big sludge right again. It's not going to dissolve. So saturated means that it's full in its aqueous state, meaning that there's no more ions or particles that are going to dissolve to make it like an invisible form. Unsaturated means that you can still do what? Yeah, it's not saturated yet. It's not full yet. So a paper towel, you got like a little part of it's full of water, but there's more paper towel there to wipe up more water. The first one would be a paper towel that's perfectly full of water, none's dripping out, it's perfect, it's just saturated. Supersaturated would mean, and it's a theoretical state, right? I mean, I can show you this, but you've heated up the solution so much, you've dumped solute in, and then you cooled it down. And the solutes are still hanging in solution. They don't want to be there because they're oversaturated. They're very unstable. This is the key word. It's very unstable. So if you look at it wrong, that baby's going to precipitate out. Okay? If you disrupt it, it's going to precipitate out. It's artificially hanging in solution when it truly should not be that saturated. Okay? So if my magic trick will work, I don't know. They haven't been working out this year.
Wait, what is it for supersaturated?
Just hold on for a
Why are
second.
you gonna experience?
Just trying to get this hair film off.
You don't want a little bit of experience.
Maybe. If I can. The hair film is fighting. Okay, so don't look at this wrong. Be nice. So I have a solution here. You can see it's liquid, right?
Well, I know that was a solid.
It's liquid, right?
What is it?
Is it liquid phase?
Yeah.
What is gas?
Okay, I'm gonna see if I can. This is a super saturated solution.
I've seen this before. Yes.
Oh, it's so cool.
I tap my magic wand.
Whoa.
And it's freezing.
Oh, God.
Is it cold?
Feel it.
Is it cold?
Pass it around. Please don't turn upside down. There's a little liquid in
Yeah,
there.
it's pretty cold.
It's not cold. It's warm. It's exothermic. That's what I do. And look to nurse.
Wow, it's really cold.
No, it's not, guys. Stop lying out loud.
I would never lie.
Okay, so continue passing it around, but come back to me. Okay, come back to me. We'll continue passing around, but come back to me, okay? So that was a super saturated solution. What I did was I had it, the sodium acetate, I had it dissolved in water, and I had too much in it, so it was kind of precipitated in the bottom. So I heated it up, so all the stuff dissolved. And then I set it in the back and didn't look at it and said, be a good flask. I said, stay in solution. And it stayed in solution. And then I just disrupted it. Did you guys see what I did to disrupt the...
Yeah.
I hit it, right? So what I did was you didn't see me, but on my magic wand, usually magicians don't tell their tricks, but on the end of my magic wand, there's a little crystal, and the crystal hit it, and it was like, oh no, disruption. And then it was off. Okay.
Oh.
That's what it did. Okay. No, it's sodium acetate.
If it was ice cream.
All right, so I'm gonna ask for the attention back here. Okay, look at this graph. What are the axes?
Perhaps it's all you.
Okay, so this is a solubility graph. Okay, and what you should notice is that as temperature increases, let me maybe draw on here. As temperature increases this way, what is generally happening to all this solids? Increasing.
Generally.
Name this as we go. Name this one.
Sodium nitrate.
Sodium nitrate. Potassium nitrate. Potassium iodide. Ammonium chloride. Potassium chloride. Potassium chlorate. Good. But if I go to the next one, this one's a little bit different. Okay. Look at the gases here. Actually, you guys tell me which ones are the gases. The dashed lines, very good. So what is happening to the solubility of gases as temperature increases?
They're all going down.
It's going down, right? So HCl gas, like hydrogen chloride gas is going down. What's this one? What's that? And what's in H3? Cat P. Ammonia, okay. And then what is SO2? SO2. It's not an ion, guys. Sulfur.
Dioxide.
Thank you. All right, guys, hush. Thank you.
So you said ammonia is capsule, so does that mean that like in Windex is the same thing? So you could clean your windows too.
Yep. Okay. So going on. Do you guys know this? Which salt solubility is least affected by temperature changes? Look at the graph.
NaCl.
NaCl, good. Why do you say that, Luke?
Because it has the.
Will, I keep doing this. It's something from the beginning of the semester I messed up in my head. So it's because there's little change in slope, right? Slope. So there's little change in slope. As you increase temperature, the solubility doesn't increase that much. But which one has the biggest change in temperature?
Looks like the top one.
Potassium nitrate has a very large change. So I want you to write down this, maybe not the question, but write down the sentence that would answer these two questions. Go ahead. A sentence that would answer both those questions. And we'll get to the lecture notes sheet I just passed out to you in a minute. Write down a sentence that answers those two questions.
Yeah, it goes up.
Yeah. And for that one, temperature goes up, solubility goes down.
All right, back to me. Cam, help me out. For salts, what is the relationship between temperature and solubility?
Okay, well, I said as temperature increases, solids increase, but gas don't.
Hold on. Solid solubility increases. Okay? And then as temperature increases, what? Gas solubility decreases. This is solid. Okay. There's a reason behind that. It's all related to kinetic energy. We're going to talk about that in a second. Thumbs up if I can move on. This is called a what curve? Solubility curve. Everybody look at the one on your upper right-hand side. It's a little bitty one. You see it in your upper right-hand side of the paper I gave you. Okay. It does have some letters on there, but the one I'm going to put up here on the board is going to be a little bit bigger. This is the one you'd expect to see like on an exam, because it's a lot more detailed. You can see all the gas relationships, the solid relationships. This one's kind of crappy. So just deal with it because the question's correlated to it, okay? So these are the questions. Let's answer a couple of these together. I'm going to ask for us to look at our sheet here. I'm going to mark up on this graph here, okay? So here we go. On your sheet it says the line represents, okay? What does this line, in terms of the three types of solutions, unsaturated, saturated, and supersaturated, these lines should be representing which solutions? Saturated. So write the line represents a saturated solution. And that's because at each given temperature, it's telling you how much can dissolve. So it's saying I can dissolve this much at this temperature, this much at this temperature, this much at this temperature, but that's the amount that would be full. Okay? So for the next question, how many grams of KBr will dissolve in 100 mils of water at 80 degrees Celsius? Here's how you read this. Look at KBr. Did you guys find the line? Okay. So we see KBr, which is potassium what? How do you always end a really easy one? Here's potassium bromide. Okay, so we're going to look at that line, but at 80 degrees Celsius. Grant, what's the solubility at 80 degrees Celsius? Excuse me? So you're looking at 80 degrees Celsius, and you're going to draw a line up until you meet the curve. Okay, so you're going to look at, so you guys with me? Find the curve you're looking for, look at the temperature you're looking for, find a merging point, which is like, correlating the curve with the temperature that's asking for, and then go over to where the temperature, where the solubility is listed. That would be 100 grams of KBr in 100 grams of water. Okay, so the answer for the first one is 100 grams. Try the next one. I know the graph is kind of dark, so you can look on the board. All right, so for NaNO3, guys, what's the solubility at 10 degrees Celsius?
80 grams.
Okay, so let's be clear. Are you saying 80 grams in what?
80 grams of NaN3.
Good. So this is 80 grams of NaNO3 and only 100 grams of water. What does this question say? 500 mils or 500 grams of water. So you multiply by 5. Good. So you're basically multiplying. This is the solubility. This is the ratio. But it's saying in 5 times the volume. So you're going to multiply by 500 grams of water. And oh my God, is right. Okay. So water. Sorry, I didn't cancel numbers. The water cancels. How many grams is that? 400 grams of sodium nitrate dissolved in 500 grams of water. Good. All right, keep going. Try to get the rest of those. I'm leaving the graph on the board so it's easier to see.
Me? No.
I was trying to figure this out.
All right, guys, which is the most soluble solid at 40 degrees? Why do we say that? So at 40, you look for the one with the highest solubility, meaning it's the highest line. Very good. Sodium nitrate. When 100 grams of KBr dissolved in 100 mils of water at 60 degrees Celsius, what type of solution is formed? So how did you guys start this one?
KBR.
Okay, so you look at the graphic KBr.
Yes. You go to 60.
You go to 60.
You look at the solubility.
You look at the solubility, which means what am I looking at? But what is this on the line representation? What type of solution is this one? On the line. Well, saturated, supersaturated, or unsaturated? On the line.
Saturated.
On the line is saturated, right? So this is saturated right here at about 85 or 90 degrees, right? But what did it give us on the paper? It said to dissolve what?
100 grams.
So we're dissolving up here. So we're dissolving more than we should have. What type of solution is that one? Supersaturated. Very good. If it's above the line, it's supersaturated. If the scenario gives you something below the line of saturation, it is unsaturated. Keep going. So when 80 grams of sodium nitrate are dissolved at 10 degrees, 80 grams are dissolved at 10 degrees. I think we've already got this one. It's so at 10 degrees, 80 grams of sodium nitrate are dissolved. What kind of solution is that? Saturated because it's on the line. Okay.
Wait, when it's unsaturated, it's
Under the line, and super is over. Yep. All right, so go back to my website for a minute. We have about 10 minutes left. We're going to find out that we're going to help practice. So when you go on my website, you're going to go to links. Open up the laptop. Go to Cox Middle High School. Go to Honors Chemistry links. I know. I saved it here just because it was easier. Scroll all the way down to UC Unit 7, Solutions in Acids and Bases. It says Solubility Curves Quiz. It's not a quiz. It's just a quick practice. I want to make sure you're solid here.
I'm answering questions.
That's what it looks like. You good? Not in docs. Not in docs. Links. Yes, they were links.
I haven't been there.
Go down to Unit 7 under links. Get some practice in. Let's go. Ooh.